When capacitors are arranged in series, think of it. They have the same charge value. They have the same charge value. When capacitors are arranged in series, they have the same charge value. That is, the charges that flow through them are the same. Capacitors in series Number 2, that's number 1. Note number 1, this is this. Number 2 is when capacitors are arranged in parallel, the same potential difference flows through them. Please note these two conditions. We use them in series, what's it called, circuit reduction technique. We need these two identity. Now, number 1, when capacitors are arranged in series, they have the same charge value. Number 2, when capacitors are arranged in parallel, they have the same potential difference value. Sample problem. Sample problem. For the network shown below, sample problem. For the network shown below, find the equivalent capacitance, comma, find the equivalent capacitance, comma, the charge and the potential difference across each capacitor. The charge and the potential difference across each capacitor as shown below. Now listen up, please. Listen up, please. If you have to solve problem on this, listen up, please. Your first task is to get C1, C2, C3. Now, mind you, they didn't give you a value for C1, C2, C3. So, which of them should be C1? Which should be C2? Which should be C3? Please use any one. Right. So, my first solution, I will say let C1 be equal to this 3 microfarad, C2 be equal to this one here, 12 microfarad, and C3 be equal to 4 microfarad. Now, here's the thing. Some person also going to say solution C1 plus C2 plus C3. The idea is this: in your question, you are not given C1, C2, C3. So you can't just go and start saying C1 equal to this. No, you have to do on there, define them first. So I'll define them. If you choose to say let C1 be this, C2 be this, C3 be this, it's still correct. First, I'm supposed to find the equivalent capacitance. Of course, this is series arrangement for this one here. This is series arrangement. So, for series arrangement, what I have is this. I have that the equivalent capacitance is equal to 1 over, we call this C1, so C1 plus this one here, 1 over C2 plus this one here, 1 over C3. In peak values, I have 1 over equivalent capacitance as being equal to 1 over C1 is 3 plus 1 over C2 is 12 plus 1 over C3 is 4. I've said this again. The reason why I am omitting units is because the units are the same. If your units are not the same, please convert first. So I'm having 1 over CEQ. This one here, 3, 12, 4. My LCM is 12. 12 over 3, 4 times 1, 4 plus 12 over 12, 1 times 1, 1 plus 12 over 4, 3 times 1, 3. So I have 1 over CEQ equal to this 8 all over 12. Reduce the lowest term, 2 here, 4, 2 here, 6, 2 here, 2, 2 here, 3. So I have 2 over 3 as this. So it means that 1 all over CEQ is equal to 2 over 3. To get your equivalent, we said invert. So invert this, I have that CEQ all over 1 is equal to invert this 3 over 2. So therefore, my equivalent capacitance is equal to 3 over 2 microfarad. If you want to express it this decimal, I have that equivalent capacitance is equal to 1.5 microfarad. This is part 1 of the question. Part 1 says find equivalent capacitance. Part 2 says find what again there? Charge. Let's get the charge. The charge across the capacitor. Now listen up. How do you get charge? Listen. Before you get charge, fall back to this condition here, please. Condition says that if they are in series, that they have the same one there, charge value. If they are in series, if they are in parallel, they have the same potential difference. Obviously, from my arrangement here, my capacitors are in series. So what does it mean here? They have the same charge value. So question, what's the charge value? I will go back to my initial equation. Recall something. Recall this. If I have charge Q, I have capacitance C, I have potential difference V. What's the equation connected there? Q is equal to what there? CV. Alright. So use this to get the value of the charge. Now listen. For this case, we need to have that C is equal to, now listen, since I have multiple capacitances, Q equal to what there? C equivalent times voltage. So you have to, right? Use the equivalent value since you have multiple capacitances. So for this, I have that Q is equal to, this is 1.5. 1.5 of Z is micro. So it becomes 1.5 times 10 to the power minus 6. That's this equivalent times, please check, your voltage was what there? How many? 16. 16 how many? Volts. So volts means I'm not converting. If it was 16 millivolts, you know what to do. Alright, please multiply this, what do you have? Please, punch, what do you have? 2.4 10 to the power minus 5 units. Coulomb. Alright. Listen, I wasn't asked to find the charge. I was asked to find what there? The charge for each capacitor. That means from here, I was asked to find the value of Q1, Q2, and Q3. Find the charge for each of them. Now, here's my condition. We said since they are arranged in series, what happens there now? They have the same charge value. So therefore, it means that Q is equal to Q1, is still equal to Q2, is still equal to Q3. The same charge value. Why? Series arrangement. So therefore, it means that Q1 is equal to this value. For physics sake, please, can we express this in terms of a prefix? What will it be? Can we express in terms of a prefix? What will it be? Note that your prefixes are in threes. Milli, mega, whatever, they are in threes. That's 3, 6, 9, minus 3, minus 6, minus 9. So express this as a prefix. What will it be? No. To make this my micro, am I multiplied by 10 or divided by 10? Huh? This is to minus 5. Let's say I want to make it minus 6. Will it be 0.24 or 24? Obviously, if I want to make this minus 6, I have to move it this way. So it becomes 0.24 times 2 power there minus 6. So it becomes 0.24 microcoulomb. That's it. Please be careful. It's you're dividing by 10, don't multiply. Alright, but that's by the way. So we can say this is 2.4 times 10 to the power minus 5 coulomb. Is still okay. Q2 equal to 2.4 times 10 to the power minus 5 coulomb, and then Q3 equal to 2.4 times 10 to the power minus 5 coulomb. So I have this. Alright. This is this. The third part of the question. Now the question says find number 1, equivalent capacitance. Number 2, the charge across the network. Number 3, the potential difference across the network. Now listen. It was a series arrangement question. So it means that the charges were the same. For series arrangement, the potential difference is not the same. They differ. Please. My question now is to get potential difference. Please check your formula. We said V is equal to what there? Q over what? C. So if you've gotten the chart for each of them, Q1, Q2, Q3, my question now will get potential difference for each of them too. That's V1, V2, V3. So for this one here, now here's my formula for what we did before now. Let's get V1. So the potential difference on your C1 capacitor is equal to Q1 all over what there? C1. And that's equal to, please give me Q1 again there. What do you have? Q1. Sorry? 2.4 in micro, I mean? Micro. Sorry, this one again. 2.4 times 10 to the power minus 5 all over. Give me C1 please. 3 microfarad. 3 times 10 to the power minus 6. Please punch this correctly. What's your value? Punch this correctly please. What's your value? Please punch this correctly. What's your value? Huh? 8 what? 8 volts. Right. Let's get V2. V2 will be equal to, from the same concept, Q2 over C2. That's equal to, Q2 is a constant, the same thing here. So 2.4 times 10 to the power minus 5 all over C2. Please recall C2 for me. 12, right? 12. So 12 times 10 to the power minus 6. 12 micro. So I have that V2 is equal to how many? 2 volts. 2 volts. Finally, V3. So the potential difference on the third capacitor V3 is equal to Q3 over C3. And that's equal to Q3 is how many there? Same thing here. 2.4 times 10 to the power minus 5 all over. C3 was what? 4. 4 times 10 to the power minus 6. 4 micro. That means V3 is equal to how many? 6 volts. So here's your thing. For series arrangement of capacitors, they have the same value for charges, but different value for what? The potential difference. That's it. Look up this. One last thing on this. One last thing on this, please. Here's the thing. Listen. If I look at the concept of capacitors, I have only 3 parameters I play with majorly. That's your charge Q, your capacitance C, and your potential difference V. These are like the 3 things I play with. Question: can I introduce current to this? How? What's the formula? V equal to IR. Where's the R from here? If you say IR, where's R here? Where's resistance here? Huh? V equal to IR, that's Ohm's law. No problem. But where's the R? There's no resistance here. So, if you say V 16 equal to I, there's no I here. R resistance, there's no, so you're open with 2 unknowns, which is not possible. So how do I introduce current to this? Because in the exam, they ask to find current. So how do you find current? Take down, please. Take down. Now listen. V equal to IR is Ohm's law under the resistor arrangement. For capacitor arrangement like this, there is also another form of Ohm's law for this. Take that, please. Ohm's law, in quotes, for a capacitor is given by Ohm's law for a capacitor is given by I equal to C dV over dt. We'll come back to calculus. Ohm's law for a capacitor circuit is given by I equal to C dV over dt. So you know what that means now, right? If they give you the potential difference in terms of time, you differentiate. But don't worry, this one is not maths. They won't give you the equation. They'll just say, find the current at so seconds. Okay. From your question, take down. We've done I. Take down please. IV. Find the current in the circuit. Find the current in the circuit after. Find the current in the circuit after 20 seconds. Find the current in the circuit after 20 seconds. We have to find I after t equal to 20 seconds. For this case, look up. For this case, it's as easy as this. For this case now, please check. We found equivalent capacitance to be how many? 1.5 microfarad. So I'm asked to find current. So for this one, I now say recall that Ohm's law for a capacitor circuit is I is equal to C dV over dt. In this case, what to do is simple. It's now equal to, this becomes not just C but what there, equivalent. Since I have several capacitors, 1, 2, 3. So I will be equal to the equivalent capacitance, then dV all over dt. Hence, I will be equal to, equivalent is 1.5 times 10 to the power minus 6. That's micro. Multiplying dV by dt. Now, for this one here, don't really bother about differentiation because you don't give an equation. Just put what there, V over T. What's V there? 16 volts. So it becomes times 16 all over T. The time, that's 20 seconds, becomes 20. So that's equal to 1.5 times 10 to the power minus 6 multiplying, please, and what do you have here? 6 over 20, what do you have? 0.8. 0.8. 0.8. Please multiply for me. I is equal to, what do I get? 1.2 power minus 6 what? Ampere. So I is equal to 1.2 micro ampere. Right, this is what you have. But this is how I find current for capacitor circuit. Always remember this formula. Now that's one, listen, that's one. Number two, bear in mind that T must be in what there? Seconds. T must be in seconds. So assuming they are said after 15 minutes. Find the current in the circuit after 15 minutes. Please, 15 minutes is how many seconds? Huh? What am I doing here? Am I multiplying? By how many? So it becomes 15 times 60. How many? 900 seconds. Please don't forget. If they say after so time, if the time is in hours, convert to seconds. If it's in minutes, convert to seconds. Please. This time has to be in seconds. And that's the idea. Alright, so I think that's how you work on this, please.